5B.Projections. 5.5 Projectiles. Flip a coin into the air, heads or tails. Fire a fast tennis ball deep into your opponent's left corner with your racket 30 love. A competition high diver performs a perfect 1.5 gainer before making a clean entry into the water. Mount Etna on the island of Sicily erupts, tossing fiery bombs of molten rock into high arcs. Each of these describes projectile motion. A projectile is any flying object that is given an initial velocity and is then influenced only by external forces, such as gravity. In other words, a projectile can be propelled for only the first part of its flight, if at all. Projectiles include those objects usually associated with weapons, such as bullets, bombs, and missiles, as well as any other object that falls or is launched through air or space. A projectile's path is called its trajectory. The unpowered portion of a projectile's flight is called a ballistic trajectory. A ballistic projectile is assumed to have only gravitational force acting on it. For simplicity's sake, we will disregard the effects of air resistance unless otherwise noted. This is a reasonable assumption for relatively slow-moving, small, dense objects. 5.6 Horizontal Projections. In Chapter 3, you studied the free fall of a dropped projectile. The path of motion was linear, and there was only one component of motion, parallel to the y-axis. A one-dimensional coordinate system was adequate for this kind of motion. However, if you kick a pebble off the top of a stairway, for example, you have another dimension to consider. As the pebble leaves the toe of your shoe, it is moving horizontally. In the total absence of gravity, ignoring air resistance, the pebble would continue at the same velocity indefinitely. However, because of the presence of gravity, the pebble also begins to fall vertically. A horizontal projection is motion in which an object is initially propelled horizontally and then allowed to fall in a ballistic trajectory. The kinematics of the vertical and horizontal components of motion are completely separate, but they occur simultaneously to give a smooth, continuous path. Figure 5-9 compares the position of a dropped object with a second object projected horizontally at the same instant. You can see that at each time, the vertical positions of both objects in the stroboscopic photo are identical. This shows that the vertical component of motion does not depend on the horizontal component. The total velocity of a projectile at any time after launch is the vector, sum of the horizontal and vertical velocity components. The horizontal and vertical components of projectile kinematics, displacement, velocity, and acceleration, are treated as two separate one-dimensional problems to which we can apply the equations of motion learned in Chapter 3. Two quantities often of interest in horizontal projections are the time of flight, delta t, and the magnitude of the horizontal displacement, absolute dex, called the range r. 5.7 Projectile motion. Horizontal component. A projectile is ideally assumed to experience no horizontal acceleration. This is not really a valid assumption because air resistance tends to slow projectiles significantly. However, for small, dense, slow-moving projectiles, it is a good approximation. Zero acceleration in the horizontal direction means that the horizontal velocity is constant. The first equation of motion, v2 x r v1x, plus average ax times delta t, becomes the horizontal scalar component equation. v2 x shirash v1x, where v2x and v1x are the x components of the projectile's velocity. Since the velocity's x component is assumed to be constant, it will simply be called vx. The second equation of motion, x2 nourish x1 plus v1 delta t plus 1 turn 2a times delta t square, becomes the horizontal scalar component equation, x2 bar x1 plus vx delta t, where x2 and x1 are the x components of the projectile's position vectors, r2 and r1, respectively. This equation is often rearranged into its displacement form. X at x2 equal 1 h vx delta t, 5.2. The third equation of motion is meaningless when the acceleration is 0, since you would be dividing by 0. 5.8 Projectile motion. Vertical component. You learned in Chapter 4 that all objects experience a uniform downward acceleration due to gravity near the Earth's surface. The scalar value of this acceleration is g mush yer 9.81 ns 2. The initial vertical velocity of a horizontal projection is 0. The final vertical velocity of the projectile is due solely to the amount of time it has to fall. Choosing the positive direction to be upward and using the y scalar components of vectors, the equations of motion take the forms listed below. First equation, v2y sur shade g delta t 5.3. Second equation, dy, 1 2g uy, delta t square, 5.4. Third equation, dy kars vida e scour over 2 I 5.0. 5.9 Frames of reference in projections. To a person flying in the plane that dropped the hay in example 5.4, it would look as if the hay were dropping straight down. A person on the ground, however, would say that the hay dropped in an arc. Their perceptions are different because they are comparing the motion to two different references. The person on the plane uses the plane as a reference with which to compare the movement of the hay bale. The hay is moving horizontally with the same speed as the plane, so it has 0 horizontal velocity with respect to the plane. Since it does not move horizontally with respect to the plane, it appears to fall straight down due to the vertical component of its motion. The person on the ground uses the ground as a reference with which to compare the bale's motion. The hay is moving horizontally with respect to the ground at a constant speed of 190 km/h. Therefore, during its fall, it moves a considerable distance horizontally with respect to the ground. This is an example, as we discussed earlier, of the same motion being observed from different reference frames. 5.10 Projection at an angle. While some projectiles do begin with only horizontal velocity, most projectiles are launched at an angle. The horizontal and vertical accelerations are assumed to be the same as for horizontal projections. But the initial vertical velocity, v1y, is no longer 0. This difference makes analyzing the motion slightly more complicated. For example, javelin throwers launch their javelins at an angle to the horizontal. Their objective is to throw the javelin as far horizontally as possible. In other words, they try to maximize the range of their throws. Launching at an angle introduces an additional step. You must calculate the vector components of the initial velocity of the projectile in both the x and y directions. Figure 5-13 shows these vector components for a velocity vector making an angle theta with the positive x-axis. As the figure shows, the horizontal initial velocity component is v1x, share v1 cos theta, while the vertical initial velocity component is v1y sar v sine theta. You must remember to substitute these expressions for the initial velocity terms in the equations of motion for the corresponding components. Once again, do not memorize a separate set of motion equations for projections at angles. 5.11 Graphing projectile motion. A projectile's vertical and horizontal displacement components can be easily calculated from the second or third equations of motion once the projectile's initial velocity components are identified. If displacement is measured from the launch point, the projectile's vertical and horizontal position coordinates can be determined from the position forms of the equations of motion. The trajectory of the projectile may be plotted on a graph from ordered pairs of vertical and horizontal position coordinates for various times after launch. Time-ordered coordinates are ordered triples, e.g. delta x, x, y. Notice in example 5-6 that the arrow's vertical velocity is 0 at 3s, and that the AML reaches its maximum height at 3s. In other words, the arrow stops going up and starts going down, which means its vertical motion must be stopped for an instant. In that same instant, the arrow reaches the peak of its flight. These facts apply to the flight of any projectile. At the peak of its trajectory, the vertical velocity is 0. Ignoring air resistance and wind, the time it takes a projectile to go from a given height to its peak is the same time that it takes the projectile to fall from its peak to its original height. For example, 1 es before the peak of its flight, the arrow is at 39.2 meters. Exactly 1 s after the peak, it has fallen back to a height of 39.2 Mich. In other words, the trajectory is symmetrical. Another helpful fact about projectile flight is that the vertical speed is the same at corresponding heights. When the arrow rose to a height of 24.5 Mich, its vertical velocity was 19.6 Metres upward. The vertical speed was the same at the corresponding height. What kind of curve is the graph of the ballistic trajectory in Figure 5 to 16? You can identify the category of the curve by the form of equations 2 and 3 in the previous example. The independent variable delta t is squared in the second equation of motion. When the highest power of the independent variable is 2, then the equation is called a quadratic function, and its graph is a parabola. 512 range determination. In any projection, the range is determined by the time the projectile takes to fall to the ground, its time of flight, and its initial horizontal velocity. The time of flight is a function of the projectile's initial vertical velocity and its initial height above the ground. These factors are important regardless of whether you are throwing a winning pass in a football game or firing a cannon shell at a distant target. The range of the bullet calculated in example 5x7, more than 7.5 miles, is quite long compared to the typical range of a rifle bullet. This is because air resistance was ignored for this problem. Research has shown that a hunting rifle bullet can lose as much as 20% of its muzzle velocity in the first 100 meters of flight, so the assumption is not realistic. Ignoring air resistance helps clarify the basic motion concepts without unnecessarily complicating the calculations. The maximum range that a projectile can attain for a given initial speed depends on its launch angle. You could determine this angle experimentally, or you could solve a series of problems with trial angles as in example 5.7. Geometrically, the maximum theoretical range for a fixed launch speed is attained with a launch angle of 45 degrees, assuming no air resistance. Real projectiles traveling at high speeds never reach their maximum theoretical range because of drag, but this angle still yields the maximum attainable range in the absence of wind or changes in air density. Range can also be increased by elevating the launch point. This is one reason armies try to capture and hold hills in battles. 5.13. Using projectile motion to solve problems. Though warfare involves the use of ballistic projectiles like bombs and bullets, it can also use ballistic motion to provide humanitarian aid. As noted in the introduction, ground transportation is often completely disrupted in devastated regions. If there are no landing fields for winged aircraft, dropping aid packages from the air is the only option for providing assistance until ground access becomes available. In past decades, many situations around the globe, whether war in Bosnia and Afghanistan, heavy rains in Somalia and Kenya, or a tsunami in the Indian Ocean, have required aid from airdrops. When large amounts of materials need to be delivered over a broad area, fixed-wing military cargo aircraft may be used. In one method, cardboard boxes and rolled out of the backs of the planes at a relatively high altitude. This technique protects the aircraft from hostile ground fire and also allows the boxes to be torn apart by their speed through the air, scattering the packages over a large area. These individual aid packages follow a more or less ballistic path to the ground. If aid supplies are being delivered to an isolated village, the aircraft may pass at a low altitude over a clear area and drop the boxes from just a few tens of meters above the ground. The boxes cushion the fall and remain essentially intact, protecting their contents. Small parachutes are often used to stabilize the dropped materials. During the initial phases of the international response to the December 2004 tsunami in the Indian Ocean, Indian naval ships sent their helicopters into flooded coastal villages and dropped tents and food while hovering. Though airdropping supplies is not the most efficient method to provide aid to the victims of war and disaster, it often remains the only available solution during certain stages of emergency response, because road travel may be hazardous or impossible. In addition, organizing an airdrop may be much faster than organizing a truck convoy on the spur of the moment, especially if the airdrops are planned as part of the overall combat operations. Saving lives and meeting human needs are important ways to love one's neighbor.